good afternoon, and good evening. So here we are today for a couple of hours to discuss about Mbed TLS. I'm going to spend the first few minutes, not of course with a lot of slides, but just to give you some context around why we are here today. Uh, what does it mean for trustedfirmware.org? And then we will have a set of presentations from the project members in the next few hours. I'll show the agenda at the end so you get a feel of what things are lined up. It's very similar to what I had posted in the workshop invite. So to set some context, I guess most of you know where Mbed TLS is used, so I'm not going to dare to explain the technical nitty-gritties of Mbed TLS. You will hear a lot about it in the following presentations. But I just wanted to spend a few minutes. Sorry, Don, did you start recording already?
I already did.
Okay, great. Okay, so one of the main things that happened with Mbed TLS earlier this year was the project being donated by ARM into trustedfirmware.org, therefore joining other trustedfirmware.org community projects like, okay, Dan tells me my face is disoriented. Hope it's better, or I can switch off my video if that helps. Okay. Hope my audio is coming across okay.
Seems okay, yeah.
Okay. Okay. So Mbed TLS moved on to trustedfirmware.org earlier on this year, joining other projects such as Trusted Firmware A, Trusted Firmware M, Hafnium, and Opti. And just wanted to tell you a bit about why that transition happened. Of course, Mbed TLS is very widely deployed open source TLS library, but over the years, it has been very much an ARM-driven project in many senses. So whether it's the roadmap as to what features gets prioritized in terms of reviews, it mostly came from ARM people. The maintainers still happens to be all ARM employees. So right from roadmap, implementation reviews, testing, everything was very much ARM driven. And it poses its own challenges when the adoption of such a good TLS library increases. Unless it's very much driven by all the stakeholders in the project, it poses its own challenges. For example, ARM can't deliver all the things that these wide set of stakeholders needs, for example. So we need more hands in the project, more reviewers, more maintainers, in terms of what features benefits the wide variety of stakeholders. It's important to listen to all these stakeholders, and putting it inside ARM and all the decisions coming from ARM alone poses many challenges. So that was the main driver behind moving Mbed TLS to trustedfirmware.org. So it becomes an actual community project where the trustedfirmware.org members and the wider community can own the project in all aspects, whether it's the roadmap, whether it's the design of critical features, development, reviews, and testing. And I think ARM, like everyone else, is very much aware it's not an overnight process. It can't be that ARM just donates things to trustedfirmware.org and immediately the community gets formed around it. It takes a while. I think it's starting to happen. And what we want to do is have such forums where we can openly discuss about the project, what are the challenges, how we can make things better, and thereby leading to a more open collaboration on all aspects of Mbed TLS. And one thing to note here is this doesn't in any way mean that ARM is no longer interested in the project. To be honest, now we have got, I would say, the maximum number of Mbed TLS engineers from ARM working on upstream than any time in the past. So we have increased as ARM increased the number of engineers working on Mbed TLS upstream from beginning of this year, and there are more engineers who are going to work on this project in the coming months as well. So we are still very much vested as ARM in the project, but at the same time, we want to listen to the feedback we have been hearing for many years, that it's challenging to contribute to say Mbed TLS. We don't get visibility on how things are done, what is a roadmap strategy, how our API is designed, etc. And this is where we've listened and basically under the trustedfirmware.org umbrella. So for most of the trustedfirmware.org project, this is the various aspects of collaboration that we try to bring about using trustedfirmware.org as a platform. So if you look at some of these things, which those things already existed when Mbed TLS was part of ARM. It was always an open source project. It came with Apache 2 license for most aspects of the project. Uh, Most of the reviews were done openly, but as I said, most of the reviews came from ARM itself. We want to improve that by bringing on more reviewers on board. There are sessions during the workshop which talks about how you can become a Mbed TLS reviewer. Workshop, yes, today we are kicking off this workshop. If there is interest, this can lead to a more regular tech forum where there's an opportunity for US stakeholders to come and present various topics that you find challenging and the project should pay attention to. Some of the other projects like TFA, OPT, or TFM do have tech forums, which has been running quite healthy for the last several months now. So we can think about does it make sense to have a uh, more regular tech forum following this workshop. Mailing list, another important change that was brought about as part of the transition to trustedfirmware.org. So earlier, Mbed TLS used to have these Mbed TLS forums, which was mostly ARM's support team answering questions. We want to very much change that model by having this mailing list as this vibrant place where people can ask their queries on Mbed TLS, discuss various design challenges without the barriers of being part of an organization. They can openly discuss about the technical aspects of the project. So there are two mailing lists today, Mbed TLS and PSA Crypto, and every day I can see there is more and more traffic in those lists where there are very useful discussions clarifying the project, whether it's technical or roadmap or on aspects like testing. So please do join the Mbed TLS mailing list if you want to sort of continue to be very much involved in the project. Testing is another important part of open collaboration. One of the things that we are facing as a challenges today, some of the testing we have is mostly internal to the ARM infrastructure. There is only a very bare minimum Travis open test system today. So as soon as you submit patches, uh, one of the maintainers or reviewers can report, okay, there are failures in the internal test system, but you don't get to see as the person who submitted the patch where the failures are. So this is going to be fixed. So today there is the open CI for both TFA, TFM, and even Hafnium. We are going to bring about an open test system under trustedfirmware.org for Mbed TLS as well. And I think over the rest of 2020 and 2021, we want to tick box all these different aspects of collaboration around Mbed TLS. So we are in a good shape in our journey towards becoming open, truly community-driven project. So as I said, this workshop is an important milestone in the journey of making the project truly collaborative. So from our perspective or trustedfirmware.org's perspective, the major objectives of the workshop is to discuss with all the participants today how to make Mbed TLS a community collaborative project. As I said, there are a couple of sessions which talks about how does work gets scheduled today, how does the roadmap gets formed. We are starting to make all the tasks public in the GitHub Epic boards, so it's quite visible to anyone interested in the project to go and have a look at what are the tasks which are being worked on, which are the tasks which are being planned, etc. Then another important aspect is there is a huge bottleneck today in terms of the amount of review bandwidth the project has. So we are lucky enough to get increasing amount of contribution from the community towards Mbed TLS, but then it doesn't progress as fast as the contributors wants to, because there is only a handful of reviewers today who can approve those patches. So we want to no longer continue in that situation of being bottleneck. So there's going to be a session which talks about how you can become a reviewer, and if you're interested over a period of time growing to as a maintainer in the project. And the other set of presentations are going to look at some of the recent interesting changes that has been happening in the project, more around Mbed TLS 3.0, TLS 1.3, PSA crypto, etc. So we've tried to mix it up from into these two broad categories, and hopefully it will be very interesting to all of you. And finally, I'll post the agenda in the chat, but a few notes as we go through the workshop. It's not going to be death by PowerPoint, so just don't expect to be listening in for the entire duration of the workshop. You can unmute at any time if you have any questions or you want to clarify something or discuss something. I think there's enough time set apart for open discussions. And if you find the chat convenient, there'll be people monitoring the chat. So please do fire your questions in the chat if that's more convenient. I think we've got around 67 people in the call now, which is great. But if you're not speaking, please do remain on mute so that everyone can hear the speaker quite easily. As I said in the beginning, the workshop is getting recorded. It's just for people who missed today's slot, they can come in a later date in the Trusted Firmware website and listen into the workshop that's happening today. One final note, don't take this opportunity to ask the existing maintainers and contributors to do more work. I think the session is all about how do we solve some of the outstanding roadmap items jointly in a collaborative fashion. And with that, I would just bring up the agenda for today. So yes, my welcome note is over now. So we are going to enter into sessions. Some of them are 20 minutes, some of them are 30 minutes. As I said, please feel free to unmute or put your questions in the chat. Let's have an active discussion today. After around 2 hours, we are going to have a break for 20 minutes, and then we are going to come back and have a few more sessions. I've put this slot at the end of the workshop for 30 minutes in case there are more questions which we are struggling to cover in each of these sessions. Please do stay back, or reviewers, maintainers, and developers are going to hang around for the last 30 minutes in case there are more things we want to openly discuss about. Yep. Any questions so far on the agenda or anything I just said about trustedfirmware.org? No. Okay, then let's start with the constant time code presentation from Chris. So I'm going to stop sharing and pass on the baton to Chris.
Okay, thank you. Let me just share my screen. Right, there you go. Hopefully you can all see my screen now.
Yes.
Yep. Okay, so hello, I am Chris Jones, and I've recently joined the Mbed TLS team, and more recently, I've been working on the idea of constant time code and defending us against side channel attacks. And so what I'm going to talk about today is what constant time code is, why it's necessary to write it, why it's needed, why it's useful, and also how we actually go about writing constant time code, and some of the uses. So to talk about constant time code, you really need to know and understand what a side channel attack is, because at the end of the day, constant time code is simply a countermeasure against certain types of side channel attacks. And so to understand what constant time code is doing, why it's needed, we need to understand the corresponding attack. So a side channel attack is kind of defined as an attack based on information which is gained, or otherwise known as sort of leaked, from the practical implementation of a system. So this isn't usually, it's not the explicit sort of return value or sort of any error codes or anything like that that the program is doing. It's more so often from the hardware perspective. It's from the actual running of your program on a machine, on a physical machine. And it's been shown many times over the past couple of decades to break real-world encryption. It's broken AES, DES, pretty much everything that's out there, and it can do so in very fast times. Sometimes, in some cases, from a single trace of a program. So they're very powerful attacks. So there's many different types of side channel attacks. Side channel attacks themselves are quite generic, quite general. One of the main ones that we're going to be looking at today is timing attacks. And this is where an attacker can measure the execution time of a program, often cryptographic code, and it can use small differences in the execution time of that program to deduce certain secret values. These are secret keys, private keys, some MAC values, passwords, things like that, things that obviously don't want your attacker to know. Cache attacks are also quite prevalent. There's, again, many different variations on cache attacks. So one of the, so for example, there's prime and probe attacks, flush and reload attacks as well. The main idea on them is that attackers can flush the cache. They can then let the victim program run. And then when that victim program runs, it will access certain values in data, which will get transferred into the cache by the hardware. And then the attacker can then come back, re-access those values, those addresses, and it will have a fast access time if it was accessed by the victim, slow access times if it wasn't. And again, it can use that to deduce secret values. Similarly there with branch predictor attacks as well, you can prime a branch predictor to take a certain path for a program, and it will have a fast execution time, relatively fast execution time if it takes that path. Again, slow if it doesn't take that path. And it can also take advantage of things like speculative execution to, again, reveal private data. So it's all about leaking information through these different channels. There are also many more side channel attacks that exist. The ones here: power analysis, fault analysis, radio emissions, things like that, are often more hardware, like physical attacks. So I'm not going to cover them here because they're not relevant to constant time code, but we'll mention that they are there. So to start off with, to make this a bit clearer, let's go for a simple example. So this one here, where we've got a simple compare function, and this kind of function could be used to check that a MAC matches an expected value, for example. This is how C does its memcomp function, and it's simply comparing two buffers against each other. If the two buffers are equal, then it returns 0. If they're not equal, then it returns -1. And the way it actually does this is it runs through a loop. It runs through each index in the buffers. It compares the two buffers indexes against each other. If they're equal, then it carries on, checks the next index, the next byte, until if all of them are equal, then it returns 0. If at any point, however, those two buffers aren't identical, then it will return -1 and just return. So hopefully some of you will have noticed that this is vulnerable to actually a number of side channel attacks, most notably a timing attack, and that's what I'm sort of going to go through here. We're going to cover. And the real issue here is that what an attacker can do is they can keep submitting different MACs. Say that the value B is the value that the attacker submits. That will be compared against our secret value A. And if the value B is incorrect, it will just return -1 straight away immediately. And so the execution time will be very, very small. It will finish executing very, very quickly. And an attacker can measure that. And then what the attacker can do is they can keep randomizing, or they can keep choosing different first bytes to provide the program or the function until the execution time takes longer, whereby you then know that you've performed another loop. And so because the execution took longer than normal, and so the first byte must have been correct, and you can move on to the second byte and the third byte, and you can repeat this to deduce the entire value of A, which is obviously something that we don't want to happen. So the issue here is this early return, and also the statement for it, the branching there, because this will cause a variable runtime based on the secret value, which is A. So this is what we want to try and prevent. So what can we actually do against this? Well, one of the main things we can do, and one of the simplest things we can do, is we can write constant time code to eliminate timing, cache, and branch predictor attacks completely. So it's a very strong defense. It's unlikely to be broken for quite some time, and it's definitely a valuable thing to know about and know how to write. So the main concept behind constant time code is that execution time cannot depend on any secret values. This is not to say that the execution time cannot vary. It certainly can do, and almost certainly will do. However, if it varies, it has to vary on publicly available data you don't want to be leaked. So it cannot vary on any sort of private key, anything like that. So this might be a bit easier if we see how we actually do this. And so there's 3 simple golden rules that we can follow. If we follow these, then the code that we write will be constant time. So the first one is that we never want to do any branches depending on any piece of secret data. As we saw before here, we had a branch. We said if A is not equal to B, that is therefore branching on a piece of secret data. And so that's not what we want to do. We also don't want to perform any memory accesses depending on secret data. That will immediately open you up to a cache attack. We'll discuss those in a minute or two. And you also never want to perform any variable time instructions on secret data. So one of the most common examples of this is division. Division is almost always variable time. This is implemented by pretty much any architecture out there. However, this last one is actually a bit trickier because on some architectures, multiplication is also variable time. And it's not always explicitly stated which instructions are variable time, which aren't. And so this often involves having to know what architecture you're compiling for very well, and also reading assembly to ensure that the code that you write is produced correctly and doesn't have any variable time instructions in there at all. So there are some limits to constant time code, namely some of the bits that I mentioned earlier. So power analysis, radio emissions attacks, differential fault attacks are all problems. They will not be solved by constant time code, but that's okay. There are other methods to defend against those kind of attacks. And also ease of maintenance as well. So constant time code is often somewhat hard to read, especially compared to non-constant time code. And it's often quite difficult to verify to ensure that it is constant time, and so it can make it quite difficult to maintain as well. So going back to our example previously, we can see here our compare function. And so we're going to try and fix this by writing it in a constant time way by applying the rules previously. So one of the main issues we had was this early return and the branch on the secret value A, on the secret buffer A. So what we're going to do is we're going to remove this and we're going to replace it with a new variable called diff. Okay, so this variable diff is going to keep track of any differences between the buffers, and so this will be returned at the end. So as you can see, we've now inside the loop, we've gotten rid of the branch, we've gotten rid of the early return, and we've replaced it with a bitwise XOR operation, whereby we are comparing A and B to see if they are different at any point. Then we'll get a non-zero result there, and that will then be ORed into our diff variable, which will then get returned at the end. So we'll have a non-zero result in diff. If A XOR B, or if A and B are the same, if they're identical, then the result of that operation will be 0. It will always be 0. And so diff will return 0 at the end if every byte in both buffers are identical to each other. And so that completely eliminates our timing attack from earlier. And so that's very good. It does, however, incur a slight performance hit, although it's not too bad in this instance, because what it will do is it will never return early, so it will always check the whole of the buffer, whether it's incorrect or correct. So yeah, there's a little bit of a trade-off there. So we'll look at another quick example here. So this is of a table lookup, and this looks quite benign when you first look at it. It's simply accessing an array. It's a simple one-line function. It should be very simple. But this is actually vulnerable to a cache attack. The issue here is that when we when we perform this access with the index I, our secret index, secret I, the hardware will actually store this address in the cache. And so if an attacker is monitoring this, they'll be able to see that this path was taken and that happened, and they could potentially use that to deduce our secret value, our secret index there, I. And so that's obviously not what we want. And we can also see that it violates rule number 2 from earlier. It performs a memory access dependent on a piece of secret data, which is the secret index here. So to fix this, we can write a function like this. Now this might look a bit confusing at first glance. It's not too bad, I assure you. So what we're doing here is we're now accessing the entire table. So we're going through every element of the table, and we are then only storing the requested index that we actually want, and then we're returning that at the end. So that's the value R there. So the choose function, let's say the equals function even, there is simply comparing the two values and returning true if they're equal, false if they're not. And the choose function simply returns the first parameter if the condition at the end, which is the equals there, is false. It returns the second parameter if the condition is true. And so this will again, it will just keep going until it finds the index that you've requested, and then it will store that one. So as you can kind of see, this is not particularly readable compared to our one-line array access. This is not nowhere near as simple. It's 4+ lines now, so that's obviously a bit of an issue there. There is also a performance hit now because we are now accessing the entire table every single time, which again is not good. For small tables, it shouldn't be too big of an issue. For large tables, it could be a bit of a problem. And you've also got the issue here that this might actually not be constant time, because there is a small chance that your compiler could just compile this whole and optimize this whole function away and just turn it into a single array access, which again, you get back to then the issue that you had before, and you haven't actually solved anything, which is always an issue. But yeah, as I say, this is now, or should be safe, because you're now storing the entire table in the cache instead of just your one value. So an attacker won't be able to tell what you've actually done there. So it'll always be the same result. So I'll just quickly mention what we actually do with Mbed TLS to protect it. So we do write constant time code. There are certain functions that are written in this sort of way. However, it's mostly written on an ad hoc basis. We only really write or rewrite particularly vulnerable functions which we know are going to cause an issue and are going to be unsafe. And this means that it's not universal to the whole library. The whole library is not written in a constant time code way. And this is because constant time code, as you probably saw there, it's quite hard to write. It's quite hard to maintain. It's not the simplest thing to do. It's also validated via manual code review, so we have to check all these individually. This usually involves checking the assembly as well. So it does take a fair bit of time to ensure that you've got it correct. We are also on the lookout for automated methods. I've done a bit of work on this myself to try and make this process a bit simpler and a bit easier to do. I will also mention that some functions are protected by blinding. This is where we essentially try and hide sensitive inputs and outputs to functions that we know are vulnerable. This is an effective method where some functions are particularly difficult to write constant time code for. And again, we're essentially sort of encrypting, not really encrypting, but somewhat encrypting the data that we feed into the function, so that if an attacker retrieves that data, they can't do anything with it anyway, because it should be useful or useless to them. So that is also done. I'll just whiz through some real world examples here. So 1996 was, I think, one of the first real timing attacks or timing attack papers. This was when it was really first discovered that it could be an issue and it could affect real world systems. 2003, we had a paper showing that timing attacks were able to be done remotely. So a big step up in severity, showing that this was a real issue. 2011, we had another paper by the same person saying that remote timing attacks are still practical to this day, showing that, again, real world systems are vulnerable. This is something that we really need to fix. 2013 was an attack called Lucky 13. This was a timing attack against TLS, and it actually broke the MAC checking stage, like I discussed earlier in our first example. 2018, you had a pair of speculative execution attacks. Spectre was a branch predictor attack, which took advantage of speculative execution to read private data that was stored in memory. And Meltdown was it was at this time, it was a cache attack, and it was able to read any piece of data in memory. So this meant any kernel data, any private data of any application whatsoever. So again, it's a very, very powerful attack. And so something that we really need to try and design against. And I'll also mention that Bleikenbacher had an attack in 1998. It wasn't originally a timing attack, but usually its variations over the past years have been. And there was a paper in 2018 which showed that I think it was about 33% of internet servers to this day are still actually vulnerable to this kind of attack, including at the time Facebook and PayPal. So again, this is something that we really need to defend against and try and stop from happening, because this is a real world issue. So just to conclude, I've hopefully shown and demonstrated that constant time code can be used to defend against a variety of side channel attacks. As I said, it's a strong defense. It's something that is well worth doing, where the trade-off is reasonable. I've also hopefully shown that constant time code is not particularly easy to write. It's prone to both human and compiler error, and is something that even when you try and write it, I know OpenSSL had an issue with this in 2016, I think, where they wrote some constant time code to fix a timing vulnerability, and they introduced another timing vulnerability with that patch. So it's certainly not easy to do, and requires a lot of concerted effort. However, there are definitely promising techniques out there to automate testing and writing of constant time code. So it's definitely possible to automate this. However, at the moment, we still need some improvements to these techniques, and we really need widespread industry adoption before these techniques can really start to be used effectively. So yes, thank you very much. So any questions at all?
Yeah, Chris, hi, this is Dave Coca. Thanks for your presentation. You mentioned that currently the writing of the Mbed TLS code is written in an ad hoc basis with regards to time constant code, and the review process of the code is manual. And I'm wondering if there's been any kind of overall analysis as to how many places in the code maybe still exist that should be considered for modification to constant time code, or if this is something that just the community needs to be on the lookout for on a regular basis.
So I myself am not, as I say, I've only recently joined the team, so I'm not personally familiar with whether that's happened. I don't think generally there has been a full scale review of vulnerable code, but I might be wrong on that one. Say if any of the other team members are here, they feel free to jump in here and correct me.
Yeah, so there hasn't been an explicit review, but over the years we developed an understanding which parts of the code are vulnerable and to which extents to these kinds of attacks. And we've been trying to address the practically exploitable issues and parts. So this means that parts that are protected by blinding are not written in constant time because they are protected by blinding. And there are other parts where we have to resort to writing actual constant time code. We normally do this on the top level where it is most exploitable and it has a bigger impact. And as probably you will see later on the roadmap, we are developing a threat model that we would like to publish. And At that point, we would like to publish an assessment about the extent we are providing protection against these kind of attacks and in which modules that happens.
Okay, great. Thanks for the feedback and info on that.
Yep, no problem. Thank you, Janos. Any other questions there?
I think there's a question in the chat, if you can see that, Chris.
Oh, I can't right now. Hang on a second. I might have to stop sharing my screen.
I think the question is, do you have tests to verify that countermeasures work, for example, with regards to timing?
Okay. So, oh, hang on. So, yes, I know we have experimented with Valgrind. In a certain way, you can abuse memory checkers in that way to kind of mark sensitive information to try and ensure that that doesn't leak. So I don't know how wide scale. I think, as I say, I don't know whether they were fully implemented in the tests, but I know they were written at one point. As for wide-scale testing to ensure that all of these countermeasures work, I don't believe there is any system out there at the moment. As I kind of previously mentioned, there are automated techniques to do this, but in many cases they lack a lot of support, and so automated testing, I think, is still a little way off from being kind of adopted at scale. So hopefully this is, again, something that's still being worked on, certainly by the academic community. It's noted as an issue, but yeah, as I say, I don't think there's too much on that at the moment, no. I hope that answered your question.
Okay, I think we can go on to the next presentation. Thanks, Chris, and for the questions.
Okay, thank you very much.
Yep. So the next talk is about the processes. As I said, we are trying to make many of the work scheduling, etc., more publicly available as part of the transition to tf.org. So we'll look at how that's being done today and what's the plans.
Hi, my name is Paul Elliott. I've not been on the Mbed TLS team entirely long. Well, okay, I joined at the start of this year, therefore it feels like I've been on the team an eternity and also no time at all. Can you see my screen okay?
Yes.
Yeah. Yes, good. Right, yes, I'd like to do a short talk about how work gets scheduled within Mbed TLS. The aim of this talk is to give you some clarity about how we plan and assess work, to show how our GitHub activity reflects that work, and explain how you, in turn, can influence our long-term roadmap. So, the planning process. So where does the work come from? Well, I mean, it comes from many sources. I mean, partially it's responding to bug reports, partially it's responding to community PRs, user requests, and then we have our own internal plans. Now, obviously, some of this work is unplanned, and indeed a great deal of the work is unplanned, which makes planning very difficult, really. But obviously, we have to have an element of planned work in there as well. Now, as we keep saying, there is not enough capacity to handle all of this unplanned work immediately. Some of this work will get done immediately, and we are attempting to try and make sure more of this work gets done immediately, but some will have to be prioritized and scheduled. So our roadmap generally only reflects the larger planned work items, and this is subject to change, obviously, according to end user needs and changing needs at that. So the basic process is this. The roadmap gives us quarterly deliverables. So community PRs and other issues and bugs are not on there, but obviously they are expected to be part of the work. The monthly sprints. So before each sprint, we spend time. We get together and we try and plan the sprint activities. And these go onto the GitHub board, which are used to track progress. Obviously, this will include items that we have seen and could not deal with immediately. So if that is considered to be of a priority, then it will be moved into the sprint as and when we feel that is the case. Obviously, we are now doing daily triage on incoming items. So this includes the bug reports and the PRs on GitHub. So typically, you should now see initial triage activity within a working day. We've experimented with various rotas to try and make sure that basically there is always someone looking and that we're not overloading single members of the team. So our aim is that small community items should get handled as they come in. At the moment, our median time to close a community PR is about 12 days, but we are actively trying to take the smaller PRs that can be done quickly and get them through. Obviously, large community items will need to be scheduled for a future sprint. As I said above, they can be backlogged, they can be prioritized. And if it's a very major item, will be added to the roadmap for later scheduling. For example, the TLS SRTP support, which is recently merged as a planned roadmap item. So how does this map to GitHub? Well, so as you probably know, the Mbed TLS repo is the main project containing pretty much everything. We also have a private repo, but this is purely for tracking security issues and security-based PRs. And when these are ready, they will be merged back into the main project. Obviously, we can't disclose details of certain issues and potential exploits until disclosure date. So we have to keep those private. There is also an Mbed TLS test repository, which holds all of our test infrastructure. As mentioned before, this is not currently public, but we are making moves to try and move this all to public repository. Until this point, again, as part of the triage, members of the team should be helping external contributors with basically what's wrong with the CI. So community issues and PRs are managed via various labels, and work is tracked by GitHub boards, and I can show you these boards. So we have a single unified board. Basically, a standard board to do, in progress, has approval, stalled for when something is getting into trouble, and done. The has approval is a particular, so we have a 2 reviewer process generally for anything other than very simple PRs, so if we're not careful, we have identified that basically a pull request can end up sitting there with 1 approval and then get stuck and isn't seen. So we're trying to make it more obvious that these are reviews. You know, it's a second review on top of a previous review, but, you know, let's try and get these through. There is also here a product backlog, and this is where we attempt to take incoming items, prioritize, and place them onto sprints. And we also have a full epic board here where we are basically larger sprints of work are broken down into individual tasks. So for an incoming issue or PR,
question that in order to navigate to the boards you just showed, it's the project tab in Mbed TLS GitHub, right?
Yes, sorry, difficult to put a link on here. Yes,
it is for the. Sorry, it is for the epics, but for the other 2s, it's on the organization, the Mbed organization projects.
Thank you.
Yeah.
So yes, for an incoming issue or pull request, triage, normally within 1 working day, as I said, will take the form of an item being labeled. And at the same time, the author may receive initial comments, feedback, and questions. Those labels may include such things as community, which obviously applies that this is a community PR or a community bug. Bug, which obviously marks this as an actual bug. The product backlog label is applied to move it to the backlog board automatically and indicates that this is a bigger task that we need to look at. Needs review and needs reviewer are, so we recently added the second one. The idea of these, although this is still being sorted, is that one means that this is just needs review. Nobody has reviewed this at all, and needs reviewer means this just needs a second review. Needs CI, obviously, all PRs require to pass the CI pushed. Needs work generally means that this PR is not in its current state suitable. Either it has broken the CI, or basically it is not considered in its current form to be what we wish. Needs change log. So as you may or may not know, we keep a log of changes which is collated together for each release. In this change log, we also obviously attribute fixes to people and keep an eye on the major changes. Not all changes need a change log. If it's a very minor change, then no. But if it's a bug fix, then generally yes. Needs backports. As you also probably know, we maintain a number of LTS, long-term support branches. Any significant bug that would affect the long-term support branches will need backporting to those branches. Generally, we try and submit a pull request and its backports at the same time. Ready for merge. This is the good one. If you have this label, then basically someone will come along and press the button soonish. Not all of the team members have the rights to do this. So basically marking this flag means that the team member who has the rights will come along and merge it. Bug appears to have appeared twice on this. Good first issue. We have started marking issues as obviously good first issues. People who are starting out on the project, whether internally or externally, these are issues that would be good to consider initially. They're self-contained. They're not too difficult. Help wanted. Again, we are trying to encourage community help with issues. If anybody wants to submit pull requests, then anything marked as help wanted would probably be a good place to start. Question is obvious. Won't fix will be applied if it's something we really do not think should be as part of the project, or we don't think is a bug, or we don't think is an issue that we are going to address. An enhancement, finally, is kind of the opposite of bug, which means it's a new feature. It's an enhancement of some form. Typically, this means that it will be unlikely to get backported to the LTS branches unless it's something that really everybody wants. But normally, this will be only in the next release. So what to watch for when you have submitted a PR? Obviously, community, because when this label gets added, you know that triage. This should happen relatively promptly. And again, normally within a working day, you will see this and other labels being added. Needs reviewer and needs review. These should be added at the same time as community. But when they disappear, you know that basically your reviews are being done. I mean, you should obviously be looking out for comments at the same time from those reviews, because there are potentially going to be requests for further work. And again, ready for merge. When you see this, you can expect it to land in the main line soon with no further work required. So to take an example, the PR gets submitted, the PR gets triaged, labels are added, community, needs review, and needs reviewer, and usually needs CI as well. But reviewers get assigned, the labels needs reviewer and needs review get removed, and the PR now has people assigned to review it. The review gets completed, needs review gets removed, it needs work, comments to the left, highlighting that we need changes before we can accept this PR. The author then updates the PR. The reviewer spots from the push that it's been updated, labels removed, needs work, label added, needs review. Review completed, label removed, needs review, label added, ready for merge. And then someone will come along and merge the PR, and the PR gets closed. So if you want to get your own features into Mbed TLS, so the main routes to influencing the roadmap, obviously we can't promise that everybody's ideas will be accepted, but we invite you to discuss this with us on the mailing list, the address of which is linked here, the new mailing list. The existing roadmap is linked here, and I can show you that very simple overview of the things which the very large features which we can expect for the foreseeable future. And this is publicly available on the Trusted Firmware wiki. Finally, submit a PR. I mean, small updates, if it's only a small thing, then hopefully that small update will go in very quickly. But for larger features, obviously the review time can be significant. So if necessary, we'll have to schedule review so that time is set aside for the feature. And therefore, you will have to wait for that to be scheduled into a future sprint. Or we invite you to collaborate. For example, Silicon Labs have been helping us with a very large range of tasks relating to hardware accelerators. They have been providing pull requests, reviews, specification work, and ongoing discussions on the design of new features. And that's it. I'm afraid to say I've gone through rather quickly. Are there any questions? Nothing at all.
Thanks, Paul. So I think that was a very quick run through on how work gets scheduled. Yeah, so we are trying to refine all these processes as time passes by, listening to all the feedback. But the main message here is, yeah, we would very much invite collaboration on all the things in the roadmap or any new contributions we would like to make. And it's not only the contributions, it's also the reviewing and sort of the growth to maintainership that also the project very badly needs. Thanks, Paul. So let's jump to the next session. So most of you know that PSA crypto has been one of the major work areas under the Mbed TLS project for the last several months. It's part of the platform security architecture program. So Jills is going to spend some time on the PSA crypto work that the project has been undertaking recently, and especially on the PSA driver interfaces. Jills, are you able to share slides?
Yes. I think you need to make me the presenter before I can share.
Okay. Don, are you getting any prompts to approve?
No, I'm not. Whoever's, yeah, no one's presenting. You should just be able to hit
Share screen.
share screen, yeah.
Okay.
Yeah.
Perfect.
All right. Can you see my presentation? My presentation title? Great. So I'm going to first of all, I'm Gilles Peskin. I've been a member of the Mbed TLS team for over 3 years, and I'm also the main architect of the PSA cryptography API. So I'm going to talk a bit about why we made this new cryptography API and how it's getting into Mbed TLS. So first of all, what's PSA? PSA is an ARM initiative. It stands, the letters stand for Platform Security Architecture. It's a platform for building secure devices, and it's something that ARM encourages. It's not there's a set of design guidelines and security architectures. It covers a lot of things, not just cryptography. It covers general operating system design, hardware design. And there's a set of programming interfaces regarding storage, application isolation, and so on, and cryptography. Cryptography is the part that we're going to talk about today. So here are some guidelines that went into the design of the API. We wanted to balance ease of use with flexibility. When it comes to cryptography, ease of use is a bit tricky because cryptography is, in some sense, not that hard to use, but it's very easy to misuse. So it's hard to use, it's easy to use incorrectly, but it's hard to use correctly. And it's especially hard because if you're not an expert, how are you going to tell whether your code is correct? Well, you test it, and okay, if your functional tests come out positive, that just tells you that your code works functionally. It doesn't tell you that your code is secure. It doesn't tell you that you've used cryptography correctly. So we've tried to make the most obvious way to use the API secure. And as much as possible, if you try to do something that's insecure, you should feel some resistance when you try to use the API. Of course, that's a very subjective feeling. So please do read the documentation. If the API is supposed to be robust, you certainly can use it incorrectly if you're not following good security guidelines. Now, in some sense, the best cryptography API is not to have a cryptography API. Quoting Thomas Ptaszek, if you're typing the letters AES into your code, you're doing it wrong, because you shouldn't have to type AES in your code. You should just say, I want to encrypt this, or even that is pushing it. You should say, I want this data to remain confidential. Just deal with it. In practice, you often have to go to a higher level of detail. Sometimes you can just use a high-level library. If you want to store a file securely, well, you open a file on the secure storage partition. You don't have to worry about how it's protected. Just say, I want to use secure storage. You want to communicate securely, well, people have designed protocols for that. When you open a web page in a browser, you don't say, well, please encrypt this web page using AES, and please verify the connection using ECDSA, and so on. You just say HTTPS, and the browser does the rest. But somebody has to implement the secure storage. Somebody has to implement the TLS protocol. And the PSA API is designed for all these somebodies who implement those higher level security solutions. So the API has to have the flexibility to implement things like the TLS protocol and IPsec and WPA and Bluetooth and GSM, and all of these protocols use different cryptography primitives. So the API exposes all of these cryptographic primitives, and that sometimes includes things that you should not use without professional guidance because they are still used in protocols. There are ways to use things like MD5 and CBC securely, even though even though those are deprecated algorithms. Banking is still using DES in some fashion, even though DES has been not actually technically broken, but it's reached its limits a long time ago. If you go a bit higher level, there's a hygiene principle which says you should only use a key for one purpose. That's a very good hygiene purpose. And then you face protocols that say, well, you have this key and it's capable of doing both encryption and signature, and the protocol requires you to do both. So the API encourages you to do the right thing, but lets you implement real-world protocols when you need them. So before we designed the API, we thought, well, can we use an existing crypto API? I didn't quote the XKCD about standards, but I'm sure most of the audience has it in mind. The good thing about standards is that there are so many to choose from. We thought, our first thought was, well, we have Mbed TLS, can we extend it? One of the main goals of extending the API was to have support for opaque keys which you don't manipulate in plain text. You just say, well, there's this key, it's in a secure element somewhere. I just have a handle to it. I don't have the key. I don't have the key material. And Mbed TLS has very transparent APIs that say, well, the key material is those bytes here. And it's difficult. It was really difficult to add support for opaque keys. We needed fundamental API changes for that. Also, Mbed TLS has been around for a long time. Our collective understanding of how to design cryptographic APIs has improved in the 15 years or so that Mbed TLS and its predecessors have been around. Mbed TLS gives you a lot of rope to hang yourself, and we wanted something which was more constraining and therefore easier to use correctly. And also the transparency of Mbed TLS means that it's hard to optimize. It's hard to plug in hardware acceleration, for example, because the data structures are open and applications can poke into data structures. You'd want to change the layout of those data structures. For example, if you plug in an accelerator and, well, you can't be sure that the application won't use it. There are plenty of other libraries around, and most of them have similar problems, that they've been around for a long time and are not easy to use. And also many of them are just too big. PSA crypto is supposed to be suitable for microcontrollers, not just for bigger systems. A pretty nice API is the one by Dan Bernstein and friends, NaCl, or its Leap Sodium variant. That's nice, but it has the problem that it's too high level. It's an API where you just say encrypt this thing, and the library takes care of choosing an algorithms and such. It's nice when all you need is to store something and get it back later. It's not nice when you need to communicate, because when you communicate, the two parties or two or more parties have to agree on which algorithms are going to be used. And this is for use on, well, microcontrollers including and other systems. So we needed something with the need something that's supported everywhere, and in practice that means C. High-level APIs won't work. If you have a Rust API and somebody wants it to use in Go, there's going to be a mismatch. Of course, there's an obvious candidate, PK611, the interface for smart cards. It's been around since pretty much forever. It's the elephant in the room in the metaphorical sense, but also kind of in a more concrete sense. PKCS 11 is big. It's really big, so we'd have to define a subset anyway. And it has some pretty complex parts. For example, you want to do something simple. I have a key and I want to use it. Well, you can't just say use this key. You have to enumerate the keys and find the key that matches the parameters that you expect. Just use this key is not a primitive in PKCS 11. It's about 4 function calls. So it's not that good for really small system. It's not easy to use, and it's also not easy to implement. There are lots of potential mistakes where you have to encode and pass parameters all over the place. So yeah, PKCS 11 is an existing standard. It's very well known, but it's not a good one for what we want to do. And so we ended up designing our own APIs, and we had a few fundamental guidelines. One of that already mentioned. It should be easy to use and hard to misuse. So keep it simple, but only as simple as it can be. Another design guidelines we had was to make it uniform. And for example, the interface to memory buffer sizes is completely uniform. Every time a function receives a pointer to a buffer as a parameter, there's an associated parameter that tells the size. You don't need to know things for example, Mbed TLS requires you to know sometimes, like, oh, this function has the same size for input and output. In the PSA API, if the function has the same size for input and output, there's an input buffer size and an output buffer size. So if the application writer doesn't know about this, there won't be a buffer overflow. Another thing that's specific to cryptography API design, the API is designed for cryptographic agility. So if you write an application and then you decide, or your security evaluator or compliance officer decides that you need to use a different cryptographic algorithm, this should be as easy as changing 1 or 2 constants in your code. You don't have to rename all of your AES functions to area functions if you want to sell your application in Korea. You just have to change 1 constant that says AES to area, and your code will start using area. Also, there's something similar to cryptographic agility, which I might call security agility. The API is just a functional API, but under the hood, it can have several implementations. I think I'll say a bit more about this later. Another thing about the functional aspect of the API, non-functional aspect, sorry, of the API, it's suitable for devices with limited resources. For example, you can process a message in multiple parts. It's more complicated, so sometimes we hesitated, should we include this, should we leave this out? And we decided to keep it in, because in the world of systems which measure the RAM in tens or hundreds of kilobytes, you sometimes need to process messages that do not fit in RAM. So you need multi-part operation. The API is designed in such a way that you can implement it without malloc. Resource allocation should be explicit. That being said, Mbed TLS currently uses malloc because we use the existing code that uses malloc. So it should be possible to write a malloc-free implementation, and we can hope maybe that Mbed TLS 4 will not use malloc, but right now Mbed TLS uses malloc, and it's not going to change very soon. And of course, when you write an implementation, you can choose which cryptographic functionality you include and which one you exclude. The API documentation itself doesn't say that any particular mechanism is mandatory. So if you want to have a device, let's take the example of a device that you sell in the US, it implements AES mode, you sell the same device into it, you implement area modes, and it'll be the same function calls, it'll be the same API, just different algorithms will be available on those two versions. So in terms of functionality, there's nothing exceptional there. It has cryptographic primitives for things like hashes, MAC, authenticated and non-authenticated ciphers, key derivation, signature, asymmetric encryption, key agreement. There are a few more things will be coming in later versions of the specification. This is what's in version 1.0 of the API. Version 1. Something will have key wrapping at least, and authenticated key agreement. Those two are coming. And in addition to cryptographic primitives, there are some basic, there is some basic functionality for key management. In particular, all keys are accessed through a key identifier. You don't say, I want to sign, and here are the bytes of the key that I want to sign with. You first say, well, I want to import a key which has these bytes, or I want to randomly generate a key, or well, depending on how you create that key. And then you get an identifier for the key. And when you want to sign with the key, you say, I want to sign with the key 112. And that means when you use a key, you don't need to care where it's stored. It could be stored in some local file system. It could be stored in RAM only. It could be stored in a secure element. And you only need to know that when you create a key. You don't need to know that when you use the key. It could be in the same memory space as your application, or it could be running in a different process, in a different trust zone world, or depending on what isolation technology is available on the device. And again, that's not something you need to care about when you're using the cryptography API. And since it's a key store which, well, stores keys, it can decide to apply policies. There's a simple policy language to express what you can do with a key once it's been created. And also the API takes care of random generation, takes care of obtaining entropy from whatever's available on your device and turning that into randomness. In addition to the application programming interface, the API that I've mentioned so far, we are actively working on a driver interface. Currently, this is the implementation is a collaboration between ARM and Silicon Labs, and Silicon Labs will give a presentation more about what they're doing right after me, I believe. The idea of drivers is you can take something like Mbed TLS, which is an implementation of the API, and which has a software implementation of a number of algorithms, and you can plug in a hardware implementation for whatever hardware is available on the device. If you have an AES accelerator, then instead of compiling the AES code from Mbed TLS, you compile the AES code that will invoke that accelerator. And from the application side, you don't need to know what's happening under the hood. It's just when you build the crypto library, when you build Mbed TLS, you say, well, I want to use this and that driver. There can be drivers for accelerators. When the driver needs to do something with the key, it receives the key, performs the operation with the key, and that's it. And there are also opaque drivers for cryptography, cryptographic engines, cryptographic processors that have their own memory space, or that their own working space, and that have their own keys, which are not disclosed outside the perimeter of that processor, and which in particular are not exportable to the application. So you can plug in opaque drivers, and then Mbed TLS will just pass the request through. It won't have access to the key itself. It just passes the request to perform some operation on the key. And there's also an entropy driver interface. This one is fairly simple, just a function that lets you query entropy from a peripheral. The way you build with a driver is that each driver comes with the implementation of some functions. For example, on this slide, there are two drivers that have a signature function, and there's each driver has a JSON specification file that describes what the driver can do. In this example, driver 1 is a transparent driver, which processes keys in clear text, and driver 2 is an opaque driver. When you compile with those two drivers, when you compile Mbed TLS with those two drivers, I should say, this is not implemented yet. It will be implemented in the coming month. When you declare at compile time that you want to use these two drivers, this generates code which at runtime will say, well, if I'm asked to use a key which is located under the purview of driver 2, the Apex driver, then call the Apex signature function from driver 2. And if not, if this is a key that's available in clear text, then call the accelerator driver, driver 1. I see a question, will the unified driver interface only support blocking calls? So far, yes. Supporting non-blocking calls ties in the library design to the OS design, and if you're on a relatively high-powered device where you can have a thread implementation, you can get around the use of blocking calls by using multiple threads. If you're on a device that's so limited that threads are not a practical option, we're not going to come up with an API that satisfies all use cases. So if you have a device that's too resource limited, you might need to use a more ad hoc API that I think we're not going to be able to standardize. That being said, Mbed TLS does currently have a feature which allows certain operations to be paused and resumed, and we are looking into extending that to the PSA API. Whether it's practical to extend that to the driver API, I'm not sure. For those of you who know this feature, it's called restartable elliptic curve operations, Mbed TLS ECP restartable, which is not currently supported in the PSA API, but should be at some point in the future. So this actually segues into crypto API support in Mbed TLS. The first release of Mbed TLS that had partial support for crypto APIs was Mbed TLS 2.17. And since then, we've added support for a few more features. And this is an ongoing effort. Performance, and especially code size, is not as good as the legacy API. because the PSA API functions are currently implemented on top of the classic Mbed TLS API. So there's an additional wrapping layer. In terms of execution time, this is pretty much imperceptible. This is pretty much negligible, but in terms of code size, there is extra code size. When we sometime next year, we're going to release Mbed TLS 3.0. We'll talk more about this a bit later today. And in 3.0, we'll have some API changes. And those API changes will allow us to make the PSA crypto API more primitive and the Mbed TLS API derived from it. So this will let us improve the performance and especially the code size of PSA code path. And at some points, classic APIs are instead going to be wrappers around PSA calls. And so they are going to have the increased code size sometime later in the 3.x series. And in terms of functionality, well, I've already mentioned an example of one of the few major features that Mbed TLS has and are not yet accessible through the PSA API. And that again, that's going to improve partly with 3.0 and partly just over time, whether it's in 2.x or 3.x. I think the slides will be published somewhere. I don't really have anything to read out here. Just once the slides are published, these are some handy links to PSA as a whole, to a place where you can read PSA crypto specifications, to Mbed TLS, of course. If you want to use Mbed TLS and PSA crypto on a real device, one way to use this is via Trusted Firmware M. And one more thing, we welcome feedback on both on Mbed TLS and the API design. There's a PSA crypto mailing list on Trusted Firmware, just like there's an Mbed TLS mailing list. If you have feedback on the PSA API, on the PSA crypto API, please send it to the PSA crypto mailing list. Although if you post it on GitHub or on the Mbed TLS mailing list, I'm sure someone will see. And if you want to drop us confidential feedback, you can email us at mbedcrypto@arm.com. If we receive feedback that way, we'll keep it confidential. What you send us might end up in the API, but we're not going to say exactly. We're not going to say why you need it or who you are if you ask us confidentially. Right. I seem to be missing this thank you slide at the end, but thank you. Are there any questions?
Okay, yeah, feel free to post questions in the chat if you want to post it later on. And we've got a session at the end as well if people want to hang around for more open discussions. Thanks a lot, Gilles. It was very informative. So we've got one more presentation before we have a short break. Many of you might have heard by now from Paul and Gilles that the project has been having a great collaboration with Silicon Labs around the PSA crypto driver interface. There has been a lot of effort from Silicon Labs around it over the last few months. So we've got Henrik and Steven from Silicon Labs to talk about the collaboration on their MCUs. Henrik, we can see your slide now.
Yeah, that's good. Many thanks, Shibu, and many thanks for this opportunity to speak virtually at this workshop. So my name is Henrik, and I'm managing the platform security R&D team at Silicon Labs in Oslo. And I'm going to talk a little bit about why we are interested in the PSA Crypto project. With me today, I have Stephen Corman. Are you out there somewhere, Stephen?
Yes, I'm here.
Perhaps you want to briefly introduce yourself?
Sure. So my name is Stephen Corman. I'm the lead developer on Henrik's platform security team at Silicon Labs.
All right. So we only have 20 minutes here today to talk about what we're doing on PSA Crypto. And so because the segment is so short, it would be great if you could just maybe save the questions until the end. Should have about 10 minutes on the end, at the end if you have any questions. So that's the agenda right there. I'm going to cover the why briefly. And then Stephen will do what he's doing best, which is the what. And then at the end, I will wrap up with a little bit on the release itself and some remarks on the collaboration model. So first of all, I just wanted to go through the evolution of our devices just for context. All these products are still active and therefore relevant also under the PSA Crypto project, because a new solution must of course handle all the hardware that is currently in production. So if you first look at Series 1 that launched about 10 years ago, pretty much all they have in terms of security is an AES accelerator engine. And the major driver for that series of products was not actually security, I would say. It was really low power. And the focus was to find ways that would allow the device to spend the least amount of time in active mode and sleep as much as possible. If the customer was doing any security at all, it was typically AES encryption. Series 1 roughly translates to the period 2013 to 2018. Back then, local attacks was still not a thing, but securing the pipe became more important as more wireless technologies was introduced. Crypto hardware accelerators became more feature-rich and included ECC. Limited boot protection was implemented, but root of trust was still not something we talked about back then. And then in 2018, we launched the first Series 2 product. And these products are designed from the ground up with security in mind. Here we have high-performance hardware accelerators with DPA countermeasures combined with PUF key protection technology, identity, root of trust-based boot protection, all provided as a secure element, or provided by a secure element, which is really a advanced hardware and firmware subsystem. Okay, so that's the hardware side. On the wireless solutions side, we have a similar picture where we have a lot of wireless technology and applications to support. This figure is, of course, extremely an extreme simplification, as our Gecko SDK includes solutions for Bluetooth, Bluetooth Mesh, C-Wave, and the two IEEE 802.15.4 stacks, CB and Thread. In addition to the standard-based solutions, we have significant business from proprietary wireless solutions, and we never really know what customers need in that business segment. Combined, the standards and the proprietary solutions are, I would say, using most of the functionality available in Mbed TLS today. And then combined with the memory constraints of these devices, integration and deployment of Mbed TLS as a unified crypto library for wireless stacks and hardware has been a challenge in pretty much every way. thinkable. But I would say it's also been a huge success since the introduction in our SDK in 2015. So if you look back a little bit, you know, the main reason why we selected Mbed TLS in the first place was that it did support most of the features back then we needed. Anything missing could be added on request. The hardware driver model was a good fit for our hardware accelerators. There was a solid long-term support branch strategy in place, and not at least a trustworthy vulnerability incident response process. However, when we started the Series 2 product, it was clear that the classic API couldn't support the secure key storage mechanism or functionality because the old API really didn't have the key handling support. And then in 2019, the initial thoughts around the PCA Crypto API started to emerge, and that was really a viable solution for us because the PCA Crypto API is really a platform API. It can offer enablement of anything from legacy hardware accelerators to Series 2 products with secure vault functionality. It's a formally vetted API and driver interface with wide industry acceptance, which means it's future-proof and likely to be acceptable for customers and likely to be something that the internal wireless stack teams are happy with. And not at least, Mbed TLS 2.20x and 3.0 offers a viable upgrade path because since we're already on Mbed TLS, the introduction of PCA Crypto as a secondary API makes the upgrade path easy. And this is because wireless stack teams, they have a lot of priorities, of course, and it's difficult for us to manage a port of everything at the same time. So having both APIs available in the same library is a huge advantage. All right, this is where I'm going to hand it over to Stephen.
Yeah, thank you, Henrik. So when we decided to go to PSA Crypto, we started collaborating with the guys at ARM. Henrik, you're showing stuff that probably shouldn't be shown. And so we started plotting out a way of putting our customers, which are using our version of our SDK that includes a version of Mbed TLS, and started planning on how to migrate those to the PSA Crypto interfaces with drivers that plug into PSA Crypto. So if you hit the next slide, I can show a bit of how that looks. So basically, the previous situation, right, for those of you on the call who also are hardware vendors and like us supply a version of Mbed TLS to your customers, is that you plug into hooks provided by so-called alt hooks or plugin points into Mbed TLS, and that enables you to swap out the entire Mbed TLS cryptography implementation of a specific module, be it AES or ECP or SHA or the likes, with your own implementation, with the caveat that you need to swap out the entire implementation. There's basically no pick and choose, right? So if you want to maintain some crypto in software, you'd have to copy over the Mbed TLS implementation. It basically becomes a giant pain in the ass. What we're moving towards for our next upcoming release is the PSA driver interface on the right-hand side of the screen. And this is, the way we're doing it. It can be replicated by those of you who are in a similar situation to us, or you can go about it another way. But basically what we want to show here is that there's a migration path for people who are on the Mbed TLS crypto APIs and don't necessarily want to move to PSA crypto APIs yet. However, those who want to move to PSA crypto APIs because they're using a secure element where you have keys wrapped in memory and you don't want to have them in plain text in RAM, can move to that model. So this is very much a dual interface model. So as you can see on the slide, the PSA accelerator drivers, we've chosen to be really the foundation of everything. SE Manager is something that's Silicon Lab specific, as is EMLib, and that's basically our HAL. And then you have the added component of PSA ITS, which I don't think has been mentioned specifically on this call yet. If you're not aware, it's a non-volatile storage driver that allows you to have PSA Crypto Core as the key manager, also including storage or non-volatile storage on your system. And so we basically coded our alt plugins from scratch to sit on top of our PSA accelerator drivers, meaning that we have a single code base for all of the crypto accelerator code, and then the alt plugins are basically just a tiny shim layer on top of the PSA drivers. And it's basically very similar to what the goal would be for Mbed TLS 3.x, where, as Gilles said before me, the intention is to move the Mbed TLS APIs on top of PSA Crypto OS. Today, it's very much still the opposite, where PSA Crypto builds on top of Mbed TLS software control. So just for a bit of background information, if you can go to the next slide, Henrik. As I mentioned, SE Manager is Silicon Lab specific. What you really need to take away from this is that our hardware abstraction layer doesn't expose anything more than what the hardware is capable of, and it doesn't expose anything less than what the hardware is capable of. That means it's a subpar solution for anyone who is looking for what we deliver in hardware, but also wants something more, right? So in order to enable those customers to use our parts and still do what everything that they want to do, we need that fallback that PSA Crypto is providing us that wasn't there with Mbed TLS APIs. And going to PSA Crypto basically enables us to keep that hardware abstraction layer as concise as possible and just map straight to the hardware. If you go to the next slide, I have information on the PSA accelerator drivers. As I said before, these are basically implementations on top of our hardware accelerator that hook into the PSA Crypto Core, or well, the PSA Crypto Core calls them for accelerating its operations. And as Gilles indicated before me, these aren't necessarily the only drivers on your system, right? So if you have multiple accelerators, for example, one's built into your MCU and one's on an external secure element, they can be called into in turn until you find one that can accelerate the operation that you want to be accelerated. We're basically making these drivers across all of our product lines. And so if you're running on a product that doesn't support an algorithm that you're asking it to do, then the driver just says, sorry, you can't do it. And then if you have the PSA Crypto Core configured to do fallback, it'll call either the next driver in your system if you have another one, or into Mbed TLS software implementation if you have that compiled in, where the default is that you actually have it compiled in. I also have 2 points on what transparent and opaque drivers are. However, Gilles talked about that before, so I'm not going to repeat the information. And then finally, next slide, please. The alt compatibility layer that I also indicated earlier is something that we built on top of the PSA accelerator drivers, just to keep our code base, compact and just have the implementation in one place. It does lead to a slight drop in performance, which can be dampened by compiling a project using multi-file compilation, or also known as link time optimization. However, you're gonna see some impact there. So just for those people who are looking to do the same thing, be aware of that. Of course, if you can get all your customers to move to the PSA APIs, it's not going to be as much of an issue. And we regard this very much as, you know, this is the legacy stuff that we're still carrying around, and it's going to disappear someday, hopefully soon, next year, maybe the year after. And just two quick slides on the PSA APIs versus Mbed TLS. Gilles touched on this already. I'm not gonna dive into it too deep. We really like the PSA APIs because they're easier to wrap your head around. They're grouped by algorithm category and not singular algorithms. They don't take key input directly, which enables our use case of having both opaque keys and transparent keys supported in the same system on the same API. They exist in both streaming and single shot modes, which is it has been a little bit hit and miss in Mbed TLS, and PSA rectifies that. All of your APIs return status codes, which is, you know, another good thing to do from a design perspective. If you go to the next slide, I'm just going to mention that all input and output buffers are now standardized. So it's really a lot easier and more concise of an API. That was it for me.
All right, thank you, Stephen. I'm just going to wrap up here with just a very quick note on the where and when. So the 3.1 version of our Gecko SDK, which is the first one with PSA crypto integrated with wireless stacks, will be released on December 9th. So if you're interested, stay tuned. You can find it on that date through the Simplicity Studio tool, which is our integrated and free development environment that you can download from Synapse.com. I just want to conclude this segment with a few remarks on the collaboration model. So if we look back on the overall PSA project manifesto, it says that the goals are as follows: make security affordable, make security practical at scale, security across the entire value chain, security from the ground up with consistent standards and features, and finally, an industry-wide responsibility. Security is everyone's responsibility. So those are of course very wise words. And it really makes a lot of sense to convert the Mbed TLS project to a full open source project, where the expectation is that the industry as a whole will collaborate to solve common problems and common roadblocks. But what is really needed to make sure that things are delivered according to the roadmap? I would say there are 4 things. Number 1 is really more contribution. If you need a PSA crypto and at the same time you're blaming ARM for not delivering, you may actually be part of the problem. And actually you can also be part of the solution too, which I think you will learn more about after the break. Second thing is that the remaining specification work must be wrapped up. More reviewer and maintainer bandwidth is really critical. I think the team will talk more about that also after the break. And finally, the transformation of the CI system to a fully open system is also going to be crucial. So if this happens at scale soon, I think the PSA crypto can become a huge success, and it can become the cornerstone of IT security that we are already hoping that it can be. So that's all we have. Any questions or comments? Shibu?
Yeah. Any questions in the chat, or if you want to unmute yourself?
Oh.
Okay. Thanks a lot, Stephen and Hendrik. It was a very useful view of the collaboration that your team has been having with Mbed TLS project. I'm sure that a lot of attendees are going to be inspired by the work we've done under Mbed TLS. And as you said, towards the end, we need more contributions, more reviewers, more maintainers to make event security become more scalable. Yep. Thanks again for all the questions and the presentation so far. I think this is a good time to go for a break. I'll just share the remaining agenda. So we've got around 20 minutes. So GMT, 4:10 GMT, we can restart the session. We are going to have 3 more short sessions. Stay tuned. It's going to talk about a lot of technical stuff and the contributions in general. So if you come back in, as per my clock, around 16 minutes, then we can restart the session. See you all in a bit.
I got a question on the release of the source code and the drivers. The release that we are going to do on December 9th is a source code release. So all the source code will be available in that December 9th release.
So that's the Gecko SDK release, right?
Yep.
Okay. Yeah, so that should have all the the drivers that Stephen was showing a bit earlier.
Yes, all of that stuff. Yeah. It's all included.
Yeah, so I think that will be the first example implementation using the PSA driver interface on a real product.
All right, is that true? That's cool. I didn't know that.
Yeah, unless someone is using the specification and not talking about in the project. Yeah, Silicon Labs is what we are aware of. So really looking forward to that first release on December. Okay, let's break up and sorry, were there more questions? I can't see the chat. Probably not. Okay, see you all in 15 minutes.